Hey everyone, welcome to another AP Precalculus video. Today we are going over 1.6 polynomial functions and end behavior.
All right, so these are the learning objectives. Basically, we're going to be talking about limit notation and how to use that for end behaviors. And we're also going to be looking at degree and leading terms to determine end behaviors. And we're also going to be going over a little bit of 1.5. We're going to be taking those skills from 1.5 to be doing more things such as sketching graphs, because that's pretty important in precalculus.
Now we're on to limit notation. Limit notation describes the behavior of a function as inputs approach a certain value. Limit notation is written in the form to the right, as you can see in this example. At the bottom, it explains the behavior of the function f of x as x approaches a. And you can see this from the arrow from x to a. And as the input value gets closer to the A, as x approaches A, the output value gets closer to B.
All right, so here's an example of limit notation. Right here, as x approaches pi over 2, the limit of f of x would be 2.4. So this is basically just saying as the input values get closer to pi over 2, our output values get closer to 2.4. So if we look on this graph right here, where f of x refers to this graph right here, 2.4 sine of x. And as you can see, at pi over 2, we are approaching 2.4. So as you are going along this graph on both sides, right? So from the left side, we're getting closer to pi over 2. From the right side, we're getting closer to pi over 2. We are getting closer to this output point right here, 2.4. So that's basically just what limit notation means. Instead of writing f of x right here, you could also write 2.4 sine x since it's defined. So that's just another way to write it because sometimes they might write it differently. So now we're going to be connecting limit notation and end behavior. So just a quick review. End behavior describes the function's tendency as input values either increase or decrease without bound. So as the input values increase or decrease continuously, you can think of it as like the ends of our function where they extend continuously. And we're going to have a visual representation next slide. So don't worry if that doesn't really make sense. So we're going to be connecting end behaviors to limit notation because in precalculus, we want to write end behaviors in the form that we were shown earlier in the limit notation form. So instead of using numbers, we're going to be using infinity and negative infinity to describe end behaviors of non-constant polynomial functions. Non-constant just meaning non-zero degree. Infinity is used to describe increasing continuously, and negative infinity is used to describe decreasing continuously. So this applies for both inputs and outputs. All right, so here is what we were talking about last slide. Right here, we have g of x on this graph right here. And we have x approaching negative infinity. All right, so this is called the left end behavior because we're looking at the left. On the left, the graph is going towards negative infinity because that's our negative values on our graph. So as x approaches negative infinity, as our inputs get smaller, we want to look at how our outputs are changing. Well, you can see that the graph goes down, which means that our outputs are going to be decreasing. Because as you go down a graph, your outputs will get smaller. It'll get more and more negative. So to describe that, you would just say negative infinity. So limit of g of x as x approaches negative infinity is just negative infinity. This describes the left end behavior, the left side. So this isn't the complete end behavior. To have the complete end behavior, you would want to use the right side too. You would want to include both. So you would also say x approaches infinity and then describe that. But this is just an example. Toward this, you could say as input values of g of x decrease without bound, output values decrease without bound as well. Because as you're going towards the left of our graph, the left end of our graph, our graph is going downwards, so our outputs are decreasing.
Okay, using a degree and leading term to find end behavior. The degree and leading term of a non-constant polynomial function can be used to determine the end behavior of the function. Now, in order to see what this means, let's go on to the next slide. As you can see, there's this huge wall of just information, which is a little intimidating, but don't be worried. We'll section this out. First, let's look at the left side. And as you can see at the top of the left side, it says odd degrees. For a positive leading term, it says that as the input of whatever function with an odd degree approaches negative infinity, the output will also approach negative infinity. And as polynomial with an odd degree and a positive leading term, as the input approaches positive infinity, the output will approach positive infinity as well. So this could apply to, for example, would be like just x. As x increases, the y increases because it would go 1, 1, 2, 2, 3, 3. And then it would also decrease as you go to negative infinity. Negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. And then now for negative leading terms, if the highest degree of the polynomial was odd, as the input approaches negative infinity, the output approaches positive infinity. And as the input approaches positive infinity, the output approaches negative infinity. Now, looking at the right side, we can see it says even degrees at the very top. If the polynomial has an even degree and a positive leading term, we can see that as the input of f of x approaches negative infinity, the output approaches positive infinity, and as the input of f of x approaches positive infinity, the output approaches positive infinity as well. And from this, you can sort of see there's something weird about that. They both have the same left and right end behaviors. And in the side note, you can see if the degree is even, both left and right end behaviors will be the same. So now for negative leading terms, you can see that as the input approaches negative infinity or positive infinity, it will always approach negative infinity as an output. And keep this characteristic in mind when looking at even degrees. Odd degrees, if you look at them, they always have differing end behaviors. Okay, so here we can see the polynomial m of x is equal to 12x cubed minus 6x to the fourth. And just looking at this equation without looking at its graph, we can see that the highest exponent is a 4. That means the polynomial m of x has a degree of 4, and we can see that the coefficient next to it is that minus 6 or negative 6, which means that the leading term is negative. Since the leading term is negative and the degree is even, we know that the end behavior would reach negative infinity on the left and right-hand sides of the equation. And remember, from the last slide, we noted that one characteristic of polynomials with even degrees is that they have the same left and right-hand behaviors. And you can see this on the graph too. As inputs both increase and decrease, the outputs decrease.
All right, so here is our first example. We're going to be using degree and the leading term to find the end behaviors of our polynomial functions. So we have two examples right here. Let's first look at h of x. So we want to identify the leading term, which has our degree as well. So what is the highest value in which x is raised to? Well, that would be 5 right here. So this would be our leading term. Our leading term is negative 12x to the fifth. So our degree is odd, and our leading coefficient, so therefore our leading term, is negative. We're going to be using this to identify the end behaviors. Well, let's think about the left end behavior as x approaches negative infinity. So as x decreases, our output values will increase. Our graph will be going upwards. So that just means that our outputs will be approaching infinity. Now, if we look at our right end behaviors, as x approaches infinity, because our degree is odd, we know that our end behaviors will differ on both the left and the right. And since we identified the left as going upwards, going towards positive infinity, we know that our right has to go towards negative infinity. So as x approaches infinity, our outputs will approach negative infinity. So that would be our limit notation describing end behavior for h of x. Next, we have S of x. And again, we're going to be doing the same thing. We're going to identify our leading term, which has our degree, and we want to see if our leading term is negative or positive. Well, 6 is the highest power in which x is raised, so 6 is our degree, and that would also mean 1.2 is our leading term. 1.2 is positive, and 6 is even. So since our degree is even, that tells us that the left end behavior and the right end behavior will be the same. So I find that a little bit less work for us. And since 1.2 is positive, that means the ends of our graph will be going upwards. So we'll be going towards positive infinity. And that also just means that our outputs increase without bound. So that's how you would write that. On the left side, our outputs increase. And on our right side, our outputs also increase.
Okay, example 2 now. We are going to match these functions to their respective equations. Looking at the first polynomial, f of x is equal to 1.3x minus 4x cubed. The highest exponent here is x cubed, so we know that this polynomial has a degree of 3. So it has an odd degree. And we can see that the coefficient is negative. So we know that on the left-hand side, it will reach positive infinity, and on the right-hand side, it will reach negative infinity. Now we can see two examples here that have those same characteristics. Then how will we be able to figure out which one is which? Well, we can look at the highest degree, which is 3, subtract 1 from that, and we are able to find how many curves the graph has. So we can see that 3 minus 1 is 2, and so the graph would have 2 turns. Well, between B and C, we can see that C here has these 2 turns, right? 1, 2. And since it, again, has a negative output as it reaches positive infinity and a positive output as it reaches negative infinity, it fulfills necessary conditions for it to be matched with f of x. And so the answer is C. Now for this next equation, we can see that the degree is 4 and the coefficient next to it is positive. We know that polynomials with even degrees have the same left and right hand behaviors. From this positive leading term, we can determine that the left hand and the right hand behaviors both go to positive. So no matter whether the input goes to positive infinity or the input goes to negative infinity. And so the only graph that has these characteristics would be A. Now, looking at m of x, we can see that it has a degree of 5, since 5 is the highest exponent of this equation. And since 5 is odd, we know that the equation will have differing left-hand and right-hand behaviors. And from the coefficient next to it, we can see that it's negative, so we know that the leading term is negative. And so with the negative leading term and the odd degree, we know that as the input approaches positive infinity, the output will approach negative infinity. And as the input approaches negative infinity, the output will approach positive infinity. You can see that there's 1, 2, 3, 4 turns here. Now it's a little hard to see that 3 turns here, but this last one is pretty obvious.
All right, so this is our last example for this video. We're going to be sketching a polynomial function just from using a given equation. So right here we have s of x, and we're given the equation, and we want to roughly sketch it out. So for these kind of questions, you're not really going to be able to get, every single point accurate, but we want to get the basics, and we're going to be talking about that here. So here is what you want to look out for. We want to find the zeros, so where the graph touches the x-axis. So you just look at our binomials and find what values would make each binomial equal to 0. We want the multiplicities of our zeros, so the values in which our binomials are raised to. And that's going to tell us whether our graph bounces or crosses the x-axis at that 0. So if your multiplicity is even, your graph will bounce at that 0. And if the multiplicity of a 0 is odd, it'll cross. So that's going to be important for sketching out our graphs. Leading coefficient and degree is what we've been talking about in this video, and that's going to help us determine the end behaviors. Degrees specifically will help us see if the left end behavior and the right end behavior will be the same. And then we're going to be looking at the y-intercept. You just plug in 0 for x to find the value in which the graph crosses the x-axis. So that's another point we want to look at too. So we're going to break this question down a little bit. We're going to be looking at each component, and then we're going to be taking them and we're going to be sketching it out. So just to make it a bit easier. So let's first take a look at the zeros of s of x. Well, what values of x would make each binomial be equal to 0? Let's look at this first binomial, negative 2x plus 9. Well, that would just be 9 over 2, because if you plugged in 9 over 2 here, you would get 0. So 9 over 2, it's a little easier to work with decimals on our graphs, so we're going to be saying 4.5, just to later when we graph it out, it'll be a little bit easier. So 4.5 would be one of our zeros, and then our second zero would just be 1.2, because 1.2 minus 1.2 would just be 0. All right, so these are the places in which our graph touches the x-axis. Next, we're going to be looking at multiplicities. We're going to be looking at the powers in which each binomial is raised to. So 4.5 was our 0 that we determined from this binomial right here. And this binomial is raised to the third power, which means that at x equals 4.5, we are going to be crossing the x-axis since we have an odd multiplicity. Now, in contrast, if we look at this binomial right here, where if we plugged in 1.2, you would get 0. Since it is raised to the second power, that means that the graph bounces at x equals 1.2. All right, next we're going to be looking at our leading coefficient. We want to see if it's positive or negative. So right here, you could distribute it out, but it's just going to take a long time. But if you think about it like this, you have a negative 2x, all right, to the third power. Well, a negative to an odd power is going to turn out negative, all right? And then we also have x right here. A positive value to a positive exponent will just be positive. So negative times a positive would be a negative. So ultimately, our leading coefficient is going to be negative. And the degree, well, since we have a 3 and a 2, if we add those together, we know that our degree will be a 5 after this whole thing is distributed out. So our degree is odd, which tells us that our end behaviors will differ on both the left and the right ends of our graph. Now the y-intercept, well, you just plug in 0 for x, and that will get you the value in which the graph crosses the y-axis, all right? So the value of y when x is 0. And if you calculated that, obviously you're not working with such big and strange numbers on most tests and assignments, but it's always better to work with harder examples. So if you calculated that, it would be 1049.76. And this is the output value in which the input value is 0, where it crosses the y-axis. All right, so now we're going to be taking these properties of s of x that we found earlier, and we're going to be using them to sketch out the graph. Again, our graphs won't be completely to scale, they're not going to be point by point accurate, but we will be getting the general shape, which is what we're looking for, and we want to get these important points such as zeros and y-intercept correctly. Alrighty, so I'm going to be looking at end behaviors first. I think that's probably going to help us the most starting out. So I'm going to get rid of this graph for just a second to look at our end behaviors. Our leading coefficient is negative, and our degree is odd. Odd degrees tell us that our left and right end behaviors will be differing. So I'm going to write out the limit. So on our left-hand side, we're going towards negative infinity. Our inputs are going towards negative infinity. And our right-hand side. Okay. So, since our leading coefficient is negative, that tells us that as our inputs decrease without bound, our outputs will increase without bound. And as our inputs increase without bound, our outputs will decrease without bound. So this will be the end behavior of s of x. So a rough sketch would just be like, on the left-hand side, we're going up. Our outputs are increasing without bound. And on the right side, as our inputs are increasing without bound, our outputs are decreasing, so we're going to be going like downwards. So this would be the general direction. So we want to keep that in mind. So knowing that, I'm going to roughly just use these little arrows to keep that in mind. All right. Now we want to look at our zeros. the points in which our graph will touch the x-axis. So 4.5 and 1.2. Again, this isn't really to scale. There we go. Alrighty, and whether our graph crosses or bounces depend on our multiplicities. Now at 4.5, we have an odd multiplicity, so we're going to be crossing, and at 1.2, we have an even multiplicity, so we're going to be bouncing. So I will kind of draw that out like that, just to keep that in mind. Alrighty. Now what we're going to be looking at our y-intercept. That's the value that our graph will cross the y-axis. So we calculated that it would be 1049.76. Totally not to scale. Alright, so that's where we're going to cross. And now, taking all these attributes, we're just going to sketch our graph out. Alright, so we're going to be starting towards the top on the left, because that's what our end behavior tells us. We're going to cross this y-intercept, and then we're going to bounce at 1.2, so we're not crossing 1.2. We're going to bounce, we're going to go up, and then we're going to cross 1.5 and go towards negative infinity on the right-hand side. Like so. So this is roughly what s of x would be looking like. So that's how you sketch a polynomial function from an equation. We want to look out for these points and then apply those to a graph. All right, so that is everything for 1.6 polynomial functions and end behavior.
Hey guys, remember to stay tuned, subscribe for more chicken math in the future.
Bye!
Bye!